In this video, we'll discuss about the independence of random variables and important concept about distributions of functions of random variables. Before we formally start, let's look at the following. We have learned about independence of different events. You should have known this equation. If two events A and B are independent, then the probability of event A and B occurring together equals the multiples of their individual probability. This also applies to cases where there are three or more events. In the case involving random variables, we can investigate the joint distribution for several independent random variables. Mathematically, n xi's are independent when the joint distribution of all xi's, where i is from 1 to n, equals the product of all individual probability density functions of each xi. In the case of the expectations of functions of xi's equals the product of all individual expectations of functions of all xi's. If all xi's are identical, they are independent and identically distributed random variables, which we call IID random variables. A collection of IID observations can be called a random sample from a common distribution. We now look at a simple example. Consider x1, x2, and x3, which are random samples from an exponential distribution with mean 2. The PD of the exponential distribution is fx equals 1 over 2 times exponential to the power negative x over 2. The joint PDF, therefore, is 1 over 2 times exponential to the power negative x over 2 times to the power 3. The mean of this joint distribution equals 2 to the power 3 equals to 8. After looking at an example, we can look at other important results. Let x1 to xn be independent random variables with respective means mu1 to mu n, and variances sigma 1 squared to sigma n squared. Let y be the sum of all ai times xi, where ai's are constants. The mean, variance, and moment generating function of y are as follows. The mean equals to the sum of all ai's times mu i's. The variance equals to the sum of all ai squared times sigma I squared. The moment generating function equals to the product of all moment generating functions of ai times xi. We will talk about the proof of the aforementioned results. For a case of means, it is easy to know that mu y equals to the expected value of y, which equals to the expected value of the sum of ai times xi's, as known from the definition. The constants can be thrown out from the parentheses, with xi's remaining in the expected values. We can easily come to a final result, which equals to the sum of ai times mu i's. The variance case is similar, and is also similar for a moment generating function case, and you may try them as exercises. Now we'll discuss some examples involving this concept. The first one is a very simple one, which states that if two independent random variables, x1 and x2, having respective means 5 and negative 6, and variances 9 and 16, that y equals to 2x1 plus 3x2, then the mean of y equals 2 times 5 plus 3 times minus 6 equals negative 8. The variance of y equals 2 squared times 9 plus 3 squared times 16 equals to 180. It's a very intuitive example, just to let you know about the application results in computation. Another example here describes the distribution of sums of independent chi-squared distributions. We can look at this theorem first. Suppose x1 to xn are independent random variables following chi-squared distribution with degrees of freedom from R1 to Rn respectively. If y equals to the sum of all xi's, then the distribution of y follows a chi-squared distribution with degrees of freedom summing from R1 to Rn. The proof of the theorem is as follows. Using the result mentioned in page 9, we know the moment generating function of y, myt, equals the product of all moment generating functions of all xi's. By independence, myt equals expectation of exponential to the power of sum of x1 to xm times t. The moment generating function of chi-squared distribution equals 1 minus 2t to the power negative r over 2. We then have myt equals 1 minus 2t to the power of negative summation of r1 to rn over 2, with t is more than 1 over 2. From this, we see an MGF of a chi-squared distribution with degrees of freedom, r1 adding to rn. Therefore, it finishes the proof that y follows a chi-squared distribution with degrees of freedom, r1 adding to rn. The theorem of the above example can be extended to normal distributions. Let Z1 to Zn having standard normal distributions. The double equals the sum of Z1 squared to Zn squared. Then double has a distribution of chi squared n. The result from page 15 also applies to normal distributions of any means and variances. By using the transformation that Z equals to x minus mu over sigma, we can transform x to standard normal distribution and thus using the same condition for y, this w also follows chi-squared n. With the above theorems, we can look at another example, which talks about the mean, variance, and mg of the sample mean of samples coming from the common distribution of mean mu, variance sigma squared, and moment generating function mt. To recall, the sample mean x bar equals the sum of xi's over n. The mean of x bar is sum of expected value of xi's over n, which equals to expected value of x1, and thus equals to mu. The variance of x bar equals to the sum of 1 over n squared times sigma squared, which equals sigma squared over n. The mg of x bar equals to the product of mg of t over n, which equals to mg of t over n whole to the power n. This example shows that x bar is an estimate of population mean mu. Due to time constraint, we will take it for granted at this stage. We now come to some exercise. You should try and all to test your understanding, and it comes to the end of this tutorial.